Hello mathematicians, we're now going to have a quick review of projectile motion, and the most pertinent fact about projectile motion is that it's an example of motion in two dimensions. However, in addition to that, we are able to take the horizontal motion and the vertical motion independently of each other. The reason being that this is vector motion and vectors have no component at right angles to themselves. So in the simplest possible case of projectile motion, which is the one that we look at, the vertical motion is the result of a constant acceleration. And that acceleration is the acceleration due to gravity of value g, and if we take downwards as the negative direction, then it will have the downward sign because it's directed towards the ground, or more specifically the centre of the earth. The horizontal motion, on the other hand, is one of constant velocity, because once the projectile is launched, there's no force acting on it horizontally, and therefore no acceleration acting horizontally. So the picture is as per the one below here. So what we can see is that we have this constant velocity, so this is the red horizontal velocity vector, and we have a constantly varying vertical velocity. So it starts off at its largest value, it decreases till at the maximum height there's no vertical velocity, and then it increases symmetrically the other side, so that at the time the particle, or the instant that it's hitting the ground, then the vertical component of velocity is the same magnitude as the initial component of velocity, but the opposite direction. Now it's really useful if we can keep this picture in mind as we analyse the motion of the projectile mathematically. And it's often useful to realise that those two components, the horizontal and the vertical, can be looked at independently and combine as and when necessary. So this is the usual starting point. That horizontally the acceleration in the x direction is 0, vertically the acceleration in the y direction is minus g. Remembering that means that we have defined downwards as negative. Now that means that we can analyse each aspect of the motion independently. So given the initial conditions that we have an initial velocity vector v, or initial velocity of magnitude v at an angle theta to the horizontal, then our horizontal velocity is initially and is always, because there's no acceleration, equal to v cos theta. It's the component of v acting in the horizontal direction. So if this is v, then if this is theta, we've got v cos theta as the component out this way. Now we can then, as always, get the horizontal displacement by integrating the horizontal velocity. So if we just say that at some time t the particle will be at position x horizontally, and we'll use our extension 2 technique as opposed to the extension 1 where we get the constants of integration, then when we carry out this integration we will get that the horizontal displacement has magnitude v cos theta times t. Now vertically we can say that we start off with an initial vertical velocity of v sine theta when t equals 0, and at some time later we will have some vertical velocity. So we integrate the acceleration, and when we do that we get that the vertical component of velocity is given by this equation. And likewise, if we integrate that with respect to time, we get the vertical component of displacement. Now if you're really struggling with using the extension 2 notation, and I shouldn't say the extension 2 notation because it's not prescribed by the syllabus, it's just the one that I'm going to tend to use. But if you're struggling with that, for the sake of your revision, go through and convince yourself that you can find the constant of integration. Now once we have these independent components that we wish, then we can combine them according to trigonometry and Pythagoras. So for example, the magnitude of the velocity vector at any time by Pythagoras is the square root of the vertical component and the horizontal component squared, and the angle it makes to the horizontal is tan to the minus 1 of the vertical component over the horizontal component. And there are similar equations for displacement in terms of magnitude and direction. A few other things that you would recall from extension 1 would include the fact that we can eliminate time from our horizontal and vertical displacement equations. When we do that, we get a quadratic, and that tells us that the path of the projectile is parabolic. The maximum height occurs when velocity in the y direction, so y dot equals 0, and the maximum range, or the range on level ground, occurs when y equals 0, when the vertical displacement is 0. So that means, as long as we're talking level ground, that we end up landing at the same height as we started. If we were falling off a cliff or firing off a cliff, then of course that condition no longer applies. The maximum range is given, and you would have spent some time on this in extension 1, when theta equals 45 degrees, and the total time of flight, again on level ground, occurs when either y equals 0, so when we're back at this spot, or double the time that it takes to reach maximum height because of symmetry. So let's look at the projectile motion question from the 2017 extension 1 paper. So we have, I guess the key part is this diagram here, that the component of the initial velocity is magnitude v at an angle of theta, and at some point here it's talking about the necessity to get across a lake which is 100 meters wide, and then it gives you these equations, which is generous. They often expect you to derive those, but in this one we are asked not to prove these equations. And part 1, show that the horizontal range of the golf ball is this expression just here. Now you probably remember that from if you learned off equations by heart in extension 1, but we should know how to derive it. So what we want is that, assuming that the ground is level, we want the value of x when y equals 0, when it comes back to the height that it was launched from. So to find that, if we take the y equation and find when that does equal 0, then because it's quadratic we get two values, t equals 0, which is obviously when it was launched, and 2v sine theta. So if we take t as 2v sine theta, the time when it returns to the ground, put it into the x displacement equation, then we're going to get v squared sine 2 theta, just using our trig expression. Part 2 says, if v squared is less than 100g, then show that the horizontal range is less than 100 meters. So if that's the case, and we plug that into our equation from part 1, just here, we can see that it will end up cancelling out, so x is less than or equal to 100 sine 2 theta, and given that 2 theta is in the range 0 to 90, because we're not going to launch the projectile with an angle theta other than 0 to 90, then sine 2 theta, that expression will become, or is, between 0 and 1. So if it's between 0 and 1, x is definitely going to be less than 100. Now for our next part, we're given that v squared equals 200g and that the horizontal range is 100 meters. So under those conditions, we have to prove this. So if we use the fact that v squared is 200g, use the fact that the horizontal range is 100 or more, and plug that into our expression above for the horizontal displacement, then what we see is that it reduces down to sine 2 theta is greater than or equal to 1/2. And solving that equation according to our normal trig rules, where we look at the first two quadrants, then we get sine 2 theta is that, therefore theta is in that range. In the last part of the question, we want the greatest height the ball can achieve. So we know that maximum height occurs when velocity in the y direction is 0. So that means that we take our velocity in the y direction and see that that is the time for maximum height, plug it into our displacement equation in the y direction, and that then gives us, eventually, after a little bit of algebra, the value of the maximum height. And then for sine squared theta, since we know that theta, the launch angle, is between 0 and 90 degrees, pi on 2, sine squared theta must be an increasing function over that range. So we can see that it's an increasing function up to there. So our maximum value is actually going to occur at our biggest value of theta, which is 5 pi on 12. So the maximum height is 100 sine squared 5 pi on 12.